All right, everyone. Good morning. Welcome to today's ITC Colloquium. Thank you all for braving the snow as well. Okay, so our speaker today is Bellovary. She got her PhD from the University of Washington, which I think you get from some of the collaborators and the code she'll be talking about. She did a couple of postdocs at University of Michigan, Vanderbilt, and then she was the Helen postdoctoral fellow at the American Museum of Natural History. She's still a research associate there and also a professor at Queensborough Community College. And she is an expert on supermassive black holes, their growth and evolution. And so without further ado.
Thank you, John. Thanks everybody for coming. It's very charming here in the snow. Good morning. Thanks for braving that. So I want to highlight some results from a recent paper which you can find on arXiv. I have lots of great collaborators. The students are highlighted in green, and I'm going to talk about how awesome they are throughout the talk. So one of my main motivations for all of these questions I have are what are the seeds of supermassive black holes like? How massive are they? When do they form? In particular, how massive they are can tell us a lot about what the subsequent evolution of supermassive black holes are like. So depending on your favorite theory, if population 3 stars are the seeds, then their masses are 100 to 1,000 solar masses or so, and there's a bunch of them. If your favorite theory is direct collapse black hole seeds, then there's less of them and they're bigger. If your favorite theory is collapsing clusters of compact objects or stars, then maybe they're like 1,000 solar masses or so, plus or minus. Or you can make up some other thing and just draw a line in PowerPoint and say, here's what supermassive black hole seeds are like, and nobody can tell me that I'm wrong, because we have no idea really what supermassive black hole seeds are like. So this is what I want to solve. What are the seeds of supermassive black holes like? That's my motivation. But the problem is that when you build a supermassive black hole, you erase the seed history. So we don't know if supermassive black holes are formed with a bunch of small black holes and some gas, or a black hole and a bunch of gas, or a big black hole and some gas. There's not really any way to know. Once we've got our supermassive black hole, it's there, but we can't tell what it was like in the past and how it assembled itself. So that's a pain. But there are a couple places to look for clues in the local universe. One of those is AGN and dwarf galaxies, which are, since they've been being searched for in the last 10 years or so in earnest, and we've been finding evidence for them. This is one in the galaxy RGG 118, which is one of the smallest massive black holes found to date, with a mass estimate of 50,000 solar masses in this nice disk dwarf galaxy. And so this type of object can give us a hint as to what the seeds were like, because, well, we can at least gives us a lower limit here on the supermassive black hole size, like at least 50,000 solar masses is a size that you can have a supermassive black hole, or intermediate mass black hole, whatever you want to call it. Central massive black hole. People have lots of names for this. But this can give us a sort of an upper limit on what the seed mass could be. Maybe seed masses are 50,000 solar masses, or maybe it was smaller and this one grew. But finding smaller and smaller central massive black holes can give us limits as to what the seed masses are. Another source that we can look for in the local universe is off-nuclear halo sources. So this one here is called HLX1, which just means hyperluminous X-ray source number 1, I think. But what this is an off-nuclear source that's been confirmed to be within this edge-on disk galaxy that has had an X-ray luminosity at one point of 10 to the 42 ergs per second, which is really bright. And so it's almost certain that this is an accreting intermediate mass black hole. It had some periodic accretion events. It's probably off now, but every year or so it bursts. It's not quite clear exactly what is going on here, but what we think is probably happening is that there's like a dwarf galaxy that's being accreted onto this larger galaxy. The dwarf galaxy was hosting a massive black or intermediate mass black hole. Somehow accretion was triggered, and so that's what's going on here. There are definitely off-nuclear X-ray sources that are not intermediate mass black holes, and so one has to be careful when trying to identify such things. A lot of them are just hyper-accreting stellar mass black holes or other objects, or X-ray binaries, whatever. But some of them are likely to be intermediate mass black holes from merging dwarf galaxies coming into the halo of a larger galaxy. So these are two ways that I want to study intermediate mass black holes in the local universe to give us clues as to how seed formation happened in the early universe. So to do that, I use cosmological simulations with a code called Changa, which is the successor to a code called Gasoline, which is a smooth particle hydrodynamics code. Changa is very excellent and awesome, and I can tell you more about it later if you like. We have two sets of simulations that I'm focusing on today to make a sample of dwarf galaxies with black holes. The first is known as the MARVEL-ous Dwarfs, named after 4 female Marvel superheroes, Elektra, Captain Marvel, Rogue, and Storm. These are zoom-in volumes of just dwarf galaxies. So they're field dwarfs that don't have any large galaxies nearby. So they're just very, very high resolution, very excellently resolved and modeled dwarf galaxies, some of which have black holes in them. And so the other sample I have, we call the DC Justice League to give representation to the other type of comics. But also we've named these after the 4 female Supreme Court justices, Sandra, Ruth, Sonia, and Elena. And these are also zoom-in cosmological simulations, but these have a Milky Way type galaxy in the center and include lots of satellite dwarf galaxies in the surrounding regions. And so the sample that I have of dwarf galaxies with simulated dwarf galaxies with black holes includes both satellites of larger galaxies and field dwarfs that are isolated, both at very high resolution. And so this gives us a nice sample of galaxies, which we can study how black holes form and evolve, and also a dependence on environment. So the black holes in the simulations, I'll give a little bit of detail on that. They form with a mass of 50,000 solar masses from dense, collapsing, low metallicity and low molecular hydrogen fraction gas. And one thing I want to highlight is that we have a subgrid model for dynamical friction, which turns out to be very important. So in a particle-based simulation, dynamical friction isn't going to be resolved unless you have one particle that's much larger than the others. And in the case of intermediate mass black holes, the black hole particles are on a similar size as the rest of the particles. And so dynamical friction is not resolved naturally. And so we include a subgrid model for black holes based on the Chandrasekhar formula to allow them to dynamically frict more properly. So in this figure from Michael Tremmel in his 2015 paper, there's some models without dynamical friction and with dynamical friction of just tossing a black hole into a halo and watching its orbit decay. This black solid line here is the Chandrasekhar timescale, and you can see that with the dynamical friction correction, for the most part, all of the models have the black hole working their way into the center of the halo at the appropriate timescale, as opposed to without the correction, none of the black holes really do that. So this is important in order to realistically resolve the dynamical evolution of black holes. So we want them to stay in the center if they're supposed to be in the center, but if there's a merger or some interesting activity, we want them to fly out of the center and dynamically evolve realistically, and then work their way back into the center at a normal timescale. Do you have a question?
Is hydrodynamic or magnetohydrodynamic?
Not magnetohydrodynamic, just hydrodynamic.
Because I noticed that maybe some of the signatures that might have been lost might be a magnetic field. In fact, if there could be magnetic fields that power outflows like jets, maybe that could be something that could help distinguish the histories of seeds that form from differently magnetized creating material, perhaps.
That's possible. We don't include any jets or magnetohydrodynamic effects in these simulations.
But also the Chandrasekhar formula is relying on the uniform density, or basically it relates only to the local density. And once the black hole gets to a region that has roughly its own mass, it will change the dynamics of the gas in a way that dynamical friction might not. be properly calculated.
That's true. So,
What
we-
do you do?
yeah, so the Chandrasekhar formula definitely isn't perfect, and we find it to be an improvement over not using it, but it definitely could still be improved upon because there are cases where it is not really appropriate to use it. So, yeah.
Just on that, what is the mass resolution of these simulations?
The mass resolution they're a bit different for the two sets of simulations, but the gas particles are something like 6,000 solar masses in the MARVEL-ous dwarfs, and they're twice that in the DC Justice League. And the dark matter particles are another factor of 2 or so larger than that. We use small dark matter particles in order to also help the dynamical friction work out, because if the particles are too large, then they artificially scatter the black holes. So we super sample the dark matter as well. All right. So some results about how the black holes form in the simulations. This is a histogram of all these simulations combined together, all 8 of these simulations, of all the black holes that form over time. And so the seed black holes start forming very early on, even at redshift 30 or so. And for the most part, they form in a cluster and finish their formation at about redshift 10, with one exception here. There's one that forms at redshift 6 in the Electra simulation. But otherwise, they form very early on, and then they stop forming, and this is due to the requirement that black holes must form out of zero metallicity gas. And so as stars are also forming in the simulations, the gas gets polluted with metals, and then that gas can no longer meet the requirement for forming black holes. So depending on which black hole seed formation you used, or a collapse, or